Okay, so let's go down to the last question. And let me clear this. Okay, so it says 3 electric charges are arranged on an XY coordinate system as shown below. Express all answers to the following parts in terms of capital Q, lowercase q, x, d, and fundamental constants. So this is okay. So I'll go through all the steps of this question. So first of all, I'm just going to look at this picture. I'm noticing that I have a positively charged object. I have a negatively charged object. The capital Q's are indicating to me that these charges are bigger than this little q over here. And question part A says, on the diagram, draw vectors representing the forces F1 and F2 exerted on the plus q, little q charge by the big Q and negative big Q charges respectively. Okay, so so far I just have to draw arrows. I can do it. So when I look at plus Q and plus Q, that's a repelling force. So that's the force on the little q. So now I want to pretend that I am little q here. I'm little q, and what do I feel? I feel a repelling down into the right. Then little q is attracted to the negative q. So I feel an attracting force down into the left. So hopefully that's so far so good. These distances are the same and the amount of the charge is the same. So these forces are the same length because again, the distances and the charges are the same. Okay, then part B says, determine the magnitude and direction of the total electric force on the plus Q charge. So what I'm going to do next is I'm going to add these vectors head to tail. Vectors, we love them. So I've got this FQ on Q, and I've drawn it up in the upper right. And then I've got this F negative Q on Q, and I add them head to tail. And the resultant goes straight down, and I'm going to use that in a moment. I used Coulomb's law to determine how much force this vector is. So Coulomb's law is K, the first charge, the second charge, over the distance squared. The distance here I found using the Pythagorean theorem. So d squared plus x squared equals this unknown squared. And the square root, so I didn't write it out, did I? We'll just call it c squared. So c would be the square root of d squared plus x squared. But then that distance, when I put it in into Coulomb's law, I have to square it because the denominators are squared. So that's how I get this distance. Okay, now for the fun part. I'm going to use proportions to solve this. And what I've done is I've color-coded this. So D is proportional to Y. X is proportional to this purple on the right here, and the yellow hypotenuse is proportional to this yellow hypotenuse. This is why I wish when I teach geometry to like freshmen and sophomores, I always want to tell them how we use these things in physics, but they're not always super excited about it. But anyway, so you've learned about similar triangles, and these triangles are similar because the angles are the same. So they have the same proportions. So what I've done here is I've set up a proportion. I've said that the green D over the yellow square root of d squared plus x squared. So the short leg over the hypotenuse is going to equal the short leg over the hypotenuse of my force triangle. So the short leg I'm calling y, and the hypotenuse is kqq over d squared plus x squared. And then I solved it for y, so I did a little math, and then I realized that this whole vector, this whole vertical vector here, is actually 2y. So I had to multiply it by 2, and I ended up with that value. Okay. So that is something. That's pretty abstract. So then next, it says determine the electric field at the position of the Q charge, the plus Q charge due to the other two charges. Now this is cool. Electric field is defined as force over charge, force per unit charge. So all I have to do is take my answer to B and divide by Q, little q. Again, this is the definition. And just a reminder that when you're doing advanced placement problems, if you don't get a part, like let's say that you didn't solve B or maybe you didn't solve it correctly, you would still get full credit for C with me and with the College Board if you explain your thinking. So if you said, I don't know the answer to B, just call the answer to be B, and I'm going to take my answer and divide it by Q to get this answer for C. Okay, then for part D, it says calculate the electric potential at the position of the plus Q charge due to the other two charges. Okay, so electric potential is KQ over R. So that's the formula. So I could do KQ over R at this position. R would be the square root of D squared plus X squared. But here is the dealio. One of these charges is positive and one of them is negative. So when I plug in to this V equals KQ over R, one of the voltages would be positive and one of the voltages would be negative, so they would cancel. So I actually end up with an electric potential of 0. And that's the bigger idea here that we want to keep in mind is that if I have a plus Q and if I have a minus Q, and if I'm right in the middle of those, the voltage is 0. And now we're seeing that actually if I drew a line down the middle of them, like at this point too, the voltage would be 0 because those distances are the same. By the way, I just helped a student in geometry this morning with a perpendicular bisector, and now thinking about that. Okay, let's see. Let's look at part E. This is probably the most abstract and calls back limits. You don't have to use limits to solve it, but I showed the math. Charge plus Q is now moved along the positive x-axis to a very large distance from the other two charges. The magnitude of the force on the plus Q charge at this large distance now varies as 1 over x cubed. Explain why this happens. So I showed the limit as x becomes infinity. As x gets much bigger than d squared plus x squared is about equal to x squared. What do I mean by that? If I look at this triangle here, if I were to, they're saying as we get farther and farther and farther out like this with x, I'm not drawing perfectly straight lines, but hopefully you get the idea. As I get farther and farther apart, oops, that wasn't D, sorry. As I get farther and farther out, the hypotenuse gets closer and closer to being the same as x. Like D matters less and less the skinnier, the longer and skinnier this triangle becomes. So I don't really even have to do a calculation for this hypotenuse. That distance is just essentially x once you get out far enough. It's not exactly x, but it's essentially x. So that's what we're saying here, is that basically you can just drop the d. So then if you drop the d, you've got x squared to the 3/2 power, which is x cubed. Let's think about a couple of scenarios here. One scenario I want to talk about is a scenario where we have two charged plates. We love this, right? We know that the way that we get those plates charged is we would take something like a battery or a power supply, and we would hook up the battery to the charged plates, and the battery behaves like a pump, and the battery is going to take electrons off the positive plate and pump them to the negative plate. So we have conservation of charge, and we have a certain amount of charge on each plate, and it is spread out uniformly, and it creates this thing called a uniform electric field. So these two charged plates situation causes the uniform electric field. Okay, now a couple more things about this. We could, when we create this field, if I was thinking about a gravitational field, usually in a gravitational field, I'll call the floor 0 meters and I'll call the ceiling, in this classroom, it's like 3 meters tall. And what I'm trying to get at here is this idea of equipotential. Like if I'm 2 meters off the ground, my equipotential, or that line is a line of equipotential because any object, no matter what it is, if it's a ball, if it's a book, if it's, hopefully it's not my electroscope, if I put it at 2 meters, it has the same potential because if it falls to the floor, it's going to have the same speed no matter what the object is, okay? I would say that the gravitational field strength is G, is 9.81. It's got a direction, it's down. Just like up here, I've got an electric field with a direction that's down. So what if I were to name the negative plate 0 volts and the top plate, what if I were to name it, say, 20 volts? Then if I were directly in the center, I would have an equipotential line that would be 10 volts. So this sort of acts on a gradient. If I went a quarter of the way across, this would be 5 volts. And this would be 15 volts. And again, those dotted lines are called lines of equipotential. Let's see. And remember then that a volt is a joule per coulomb. So 15 volts is 15 joules per coulomb. The idea is if I took a certain amount of charge and put it right at that line, now I know how much potential energy I have per coulomb. And if I multiply, let's see, if I multiply the voltage times the charge, I'm going to get that potential energy. So that was one idea that I wanted us to get across. Another thing that you'll see sometimes is distances. So let's say for a moment that this distance is 10 centimeters or 0.10 meters. Then I could say that the electric field here, there's a couple of different ways to define the electric field, but hang on. This is one of them, that voltage is equal to electric field times distance. And so you could say that this electric field would be 20 volts over 0.10 meters, or 200 volts per meter, or 200 newtons per coulomb. And those two statements are equivalent. So we would be able to say how many volts we get per meter as we move through this electric field. And we'd also be able to say how much force is exerted per coulomb of charge. Okay, the other big idea I wanted to talk about was something with point charges. And let's just say for a minute that I had a point charge called Q, and let's say I had another point charge that I'll call 2Q, and let's say they were separated by a distance D, and let's say that I wanted to focus on some point that's not in the middle. Let's say that it's 2/3 of the way across. So this would be a point where the net force is not 0, the electric field is not 0, and the voltage is not 0. So how would I go about computing these things? To get the force at this point on some charge Q, I would need to do Coulomb's law between little q and big Q. And then I would need to do it between little q and 2Q. And then, let's see. The first one, if these are all positive, the first one is to the right, the second one is to the left, and so I would have to get the net force, I would have to subtract the smaller one from the bigger. Let's see, I'm making this up in real time, which maybe wasn't my wisest move, but if I were going to simplify this, this would be 9kq over 4d squared, and this would be, come on, how, 18kq over d squared. So this one from the 2q would be bigger. So I would take the 18 one minus the 9/4 one. What if I wanted to get the voltage? The voltage at this point. Voltage is kq over r. So what I would have to do is figure out kq over r from each charge and add them together. In this case, I would add them together because they're both positive. So it would be k big Q over 2/3 d, and the other one would be k 2q over 1/3 d. And again, I'd have to simplify that. And with voltage, if they're the same sign, if the charges are the same side, you just add them together. And now it's sort of a little bit of an algebra thing. And then, okay, one more thing. I should have said this earlier. If I wanted to find the electric field at this point, I can do that by taking the net force and dividing by little q. So once I got my answer from Coulomb's law, if I found that net force divided by little q, and that would be my electric field. Okay, I'm going to stop my recording. I just wanted to